Now moving forward, all the Arrhenius acids are the acids in the Bronsted-Lowry theory. For the comparison, we have a table here. According to this table, Arrhenius concept says that the acid is the substance when dissolved in water increases the concentration of proton ions. And the Bronsted-Lowry concept says that the acids are the proton donor. So in both concepts, acids are the substances that are releasing the hydrogen ions. So therefore all the substances that are considered acids in the Bronsted-Lowry concept are also considered acids in the Arrhenius concept. For example, if we take the example of nitric acid, when it is dissolved in water, it is dissociated into hydrogen ion and the nitrate ion. Similarly, if we take the example in which this nitric acid reacts with ammonia, it results in the formation of ammonium ion and the nitrate ion. Now, since this nitric acid is donating proton to ammonia, so here we may consider this nitric acid as a Bronsted-Lowry acid. Here, since this nitric acid is generating proton in an aqueous solution, therefore we can consider it is an Arrhenius acid. Now you may see that both species are same, and both species can be considered as an acid in both Arrhenius as well as the Bronsted-Lowry concept. We just discussed about the acids. We just compared the acids in the Bronsted-Lowry concept and the Arrhenius concept. Now we will compare the bases in the Bronsted-Lowry concept and the Arrhenius concept. The bases that are included in the Bronsted theory, except having the OH group, are not the Arrhenius bases. Here is a comparison chart for the bases in the Arrhenius concept and the Bronsted-Lowry concept. In the Arrhenius concept, the base is the substance that when dissolved in water increases the concentration of hydroxide ion. This means that for Arrhenius bases, that substance should generate hydroxide ion. This means that the substance should have OH in it. However, if we consider the definition of bases in the Bronsted-Lowry concept, then in this concept, bases are the proton acceptor. There is no limitation that the base should have the hydroxide ion or should generate the hydroxide ion in the aqueous solution. So because of this difference in definition, the bases in the Arrhenius concept and Bronsted-Lowry concept are not same, except in some cases. For example, if we take the example of ammonia here, we can see that ammonia takes proton from hydrochloric acid and is converted into ammonium ion. Now, if we apply the definition of Arrhenius concept here, then we cannot consider it as a base because it doesn't generate the hydroxide ion. However, we can consider it as a base in the Bronsted-Lowry concept because it is accepting proton from the hydrochloric acid. So here is the difference between the Arrhenius bases and the Bronsted-Lowry bases. Now we take another example in which sodium hydroxide reacts with hydrochloric acid to form sodium chloride and water molecule. Now this sodium hydroxide is a base according to Arrhenius concept because this sodium hydroxide when dissolved in water results in the generation of sodium ion and the hydroxide ion. Now, if we apply the Bronsted-Lowry concept on sodium hydroxide, then in acid-base reaction we may see here that the lone pair on the oxygen atom is accepting the proton from hydrochloric acid to form the water molecule. So this means that here sodium hydroxide is also can also be referred as the Bronsted-Lowry base. So all the bases that have OH and that can accept proton are both the Arrhenius base as well as the Bronsted-Lowry base. However, if those bases do not have OH or do not generate OH in the aqueous solution but accept proton from an acid, will only be considered as the Bronsted-Lowry base, not an Arrhenius base, as we just discussed the example of ammonia. Now moving forward, now we will do certain activities to classify certain substances as acids or bases, or as a proton donor or as a proton acceptor. We have an example in which hydrochloric acid is reacting with water molecule to form hydronium ion and the chloride ion. Now we need to identify these substances as the acids or bases. So for acids, always remember that acids are the proton donor, and the second tip to identify a substance as an acid is that after donation of proton, acids form a negative ion. Now you may see here that HCl is working as an acid here. HCl is donating proton. HCl is donating proton and has been converted into chloride ion. So here these two, you may see that these two conditions have been met: proton donating condition and the formation of negative ion. So this means that HCl is an acid here. Similarly, to identify a certain substance as a base, we need to see that if that substance is meeting two conditions, that is, it should be a proton acceptor, and after accepting proton, it should form a positive ion. Now in this example, you may see here that water is acting as a base, because the lone pair on the oxygen atom is using this lone pair, oxygen atom is using this lone pair to take the hydrogen ion and has been converted into hydronium ion. Now you may see here that it is accepting proton as well as has been converted into a positively charged species. So therefore, in this reaction, water is a base and hydrochloric acid is an acid. Let's see another example. In this example, water molecule is reacting with ammonia to form ammonium ion and hydroxide ion. We need to identify water and ammonia as acid or a base. Now you may see here that the acid, as we read before, is a proton donor, and after donation it forms a negative ion. Now see that here water molecule is donating proton to form hydroxide ion. It is negatively charged. So therefore water is acting as an acid here. Similarly, for base we read that it is a proton acceptor, and after accepting proton forms a positive ion. So here you may see that ammonia is accepting proton from water molecule and has been converted into ammonium ion. Since it is a positive ion, so this means that ammonia is a base. Now we will do a self-assessment exercise. We have to identify the Bronsted acid and Bronsted base, Bronsted acid and the Bronsted base in the following. Now adopt the same procedure as we adopted before. First we will see that which species is donating proton. It is the sulfuric acid because after donating proton, it has been converted into hydrogen sulfate ion. Now this conversion was possible only when it donated a proton or the hydrogen ion. So this means that sulfuric acid is working as an acid here, as a Bronsted-Lowry acid. And for the base, we will see that water molecule is accepting the proton from the sulfuric acid and has been converted into hydronium ion. Now, since it accepted the proton and since it has been converted into a positively charged species, so therefore that water molecule will be considered as a base here. Now take another example. In this example, acetic acids reacts with water molecule to form acetate ion and the hydronium ion. Now you may see here that acetic acid has donated the proton and has been converted into acetate ion with a negative charge. So therefore this substance will be referred to as a Bronsted-Lowry acid. Now here that water molecule accepted the proton from acetic acid and has been converted into hydronium ion, that is the positively charged species. So therefore we will consider it as an Arrhenius, we will consider it as an Lowry Bronsted base. Now here there is another example in which H2S reacts with NH3 to form NH4 positive and HS negative. Now here you may see that this substance is donating proton to form this negatively charged species, and this substance is accepting proton to form this positively charged species. So here it may be referred as the hydrogen sulfide may be referred as the Bronsted-Lowry acid, and ammonia may be referred to as the Lowry Bronsted base.